Among the four fundamental forces of nature, the weak nuclear force is perhaps the most elusive, subtle, and yet profoundly consequential. Unlike gravity, which governs the large-scale structure of the universe, or the strong force, which binds the nuclei of atoms, the weak force operates at microscopic scales, shaping the very processes that govern particle decay, nuclear transformations, and the life cycles of stars. It is the architect of change at the subatomic level, invisible yet indispensable, quietly orchestrating the evolution of matter. The weak force is responsible for phenomena such as beta decay, a process in which a neutron transforms into a proton, emitting an electron and an antineutrino. This transformation is fundamental to the synthesis of elements in stars, the regulation of nuclear stability, and the production of energy that sustains stellar cores. Without the weak force, the chain of nuclear reactions in stars would halt, preventing the fusion processes that generate light, heat, and the elements necessary for planets and life. In essence, the weak force is a silent facilitator, enabling the transformations that make the universe dynamic rather than static. Mediating the weak force are massive particles known as the W and Z bosons. These carriers are unique among force mediators because their large masses limit the range of the weak force to subatomic distances. Despite acting over an incredibly short span, the W and Z bosons are essential, transmitting the weak interaction between particles, enabling decays, and facilitating processes that break certain symmetries in nature. Their discovery in the 1980s was a landmark achievement, confirming the electroweak theory, which unifies the weak and electromagnetic forces under a single framework. The weak force is intimately connected to one of the universe's deepest mysteries, the imbalance between matter and antimatter. While the Big Bang should have produced equal amounts of each, our observable universe is dominated by matter. Experiments involving particles that decay through the weak interaction, such as kaons and bmesons, reveal subtle violations of symmetry, CP violation, that hint at why matter prevailed. In this way, the weak force is not only a shaper of particle decay but a cosmic architect, influencing the very composition of the universe and the possibility of our existence. Beyond particle decay, the weak force governs processes critical to stellar evolution and nucleosynthesis. In the cores of stars, neutrinos produced by weak interactions escape freely, carrying energy and providing vital insight into the internal workings of stars. These elusive particles, nearly massless and almost invisible, allow astronomers and physicists to probe stellar interiors, revealing the mechanisms of fusion and energy transfer that light up galaxies. Without the weak force and its role in neutrino production, our understanding of stars, supernovae, and cosmic evolution would be incomplete. The weak force also demonstrates the subtlety and elegance of quantum mechanics. Unlike the strong or electromagnetic forces, it can change the very identity of particles, transforming one type of quark into another. This property underlies the decay of neutrons, the production of certain mesons, and the creation of rare and exotic particles in high-energy experiments. By enabling these transformations, the weak force ensures that matter is dynamic, adaptable, and capable of change, reflecting a universe in which permanence is tempered by constant transformation at the subatomic level. In extreme environments, such as supernovae, the weak force governs the behavior of neutrinos, influencing the explosion mechanisms and the distribution of elements. Neutrinos produced via weak interactions carry away energy, drive shock waves, and shape the chemical composition of the cosmos. These processes link the microscopic world of quarks and bosons to the grandest scales of stellar evolution, demonstrating that even the weakest of forces has profound and far-reaching effects. Contemplating the weak force is to recognize that the universe is not only shaped by the massive, the visible, and the obvious, but also by the subtle, ephemeral, and nearly invisible. It governs transformations that sustain life, generate energy, and dictate the ultimate fate of matter. It is a reminder that change is fundamental to existence and that even forces operating at minuscule scales can determine the composition and evolution of the cosmos. In essence, the weak force is the universe's quiet sculptor. It shapes decay, governs transformation, and ensures that matter evolves, stars shine, and life is possible. Through the W and Z bosons, through beta decay and neutrino interactions, the weak force demonstrates that even the subtlest interactions are vital to the structure, dynamics, and destiny of the universe. It is a testament to the profound interconnection between the tiniest scales of quantum mechanics and the vast scales of cosmic evolution. Reminding us that in the quantum realm, even the weakest force wields immense power.